Today, I'd like to present my project, a comparative study of techniques for non-photorealistic imaging. First, what is non-photorealistic imaging or rendering? It is an area of image processing that focuses on creating artistic, abstract, or stylized visuals rather than photorealistic ones. Over the years, many approaches have been developed, ranging from edge-aware filtering techniques to more complex methods that leverage multiple input images. This project focuses on re-implementing and comparing two methods for creating non-photorealistic images. The first method is domain transform. It is a single image approach that uses fast, edge-preserving filters to produce stylized outputs such as pencil sketches and watercolor effects. It achieves its efficiency through a fundamental insight. An RGB image can be viewed as a 2D manifold embedded in a 5D space, where an edge-preserving filter operates as a 5D spatially invariant kernel. This transform establishes an isometry between curves on the 2D image manifold and the real line, maintaining geodesic distances and adaptively warping the signal for efficient 1D edge-preserving filtering in linear time. The second method utilizes multi-flash imaging. By using multiple images captured under varying lighting conditions, this method detects depth discontinuities to create highly detailed stylized outputs. It can capture a series of images of a scene, each illuminated by a different light source positioned near the camera's center of projection. Then, the shadows formed at depth discontinuities can provide a reliable cue for constructing depth edge maps, applicable to both static and dynamic scenes. The goal of this comparison is to evaluate the two methods in terms of their ability to generate high-quality pencil sketch-like outputs. By applying both techniques to a consistent set of input images, I aim to analyze their performance and identify their strengths and limitations. Experiments. For this experiment, I set up a detailed indoor scene in my room containing objects at varying depths to simulate a challenging environment for both methods. For the domain transform method, I captured a single photo under ambient lighting conditions, as it only requires a single input image. For the multi-flash imaging method, I positioned a phone flashlight at four distinct positions: left, top, right, and bottom. I then captured four images with the light source at each of these positions. Results. On the left, we can see the results of the domain transform method, and on the right, the multi-flash imaging result. Observations. Overall, the multi-flash imaging method produced much better results with cleaner edges, lower noise, and sharper visual details compared to the domain transform method. However, in the center part of the multi-flash method output, some objects, including the tea bottle, exhibited double edges. On the other hand, the multi-flash method can preserve the original colors of objects. By looking at the wall, the door, and the desks, we can notice that the multi-flash method does a much better job at preserving the original colors of these objects. On the other hand, however, the multi-flash method does rely on additional hardware and controlled lighting conditions, and is much less versatile than the domain transform method. Future improvements. For the domain transform method, I performed basic parameter tuning of spatial and range smoothing values, achieving satisfactory results. However, a more systematic study could explore optimal parameter combinations to balance edge preservations and noise reduction using quantitative metrics such as edge sharpness and perceptual quality. Multi-flash methods. In this experiment, I simulated the setup by manually positioning a phone flashlight at four locations. While practical for this project, this approach is suboptimal. Ideally, four evenly distributed camera flashes should be positioned around the lens and synchronized to emit light at equal and short intervals. Such a setup would minimize motion artifacts and ensure uniform, sharp shadows for accurate edge detection. In the original paper, it also proposed advanced enhancements to improve the method's performance and practicality. For instance, replacing visible flashes with invisible wavelengths such as infrared or ultraviolet light, would make the system less intrusive. Another promising improvement involves frequency domain multiplexing, where light sources operate at different frequencies, allowing multi-flash effects to be captured in a single exposure. This would enable real-time performance similar to the domain transform method, while retaining multi-flash imaging's superior edge detection capabilities. Thank you so much.